introduce our speaker today, who is Zhongwei from University of Kentucky. So Professor Sheng is a leading expert in the theory of elliptic and parabolic equations, especially in the homogenization theory. So today he's going to talk about quantitative results for Darcy's law. So Zhongwei, whenever you're ready.
Okay, thanks for the introduction. Also, thanks to organizers, particularly to Hongjie for the opportunities to speak at the seminar today. So I want to talk about something I did last year and the year before on Darcy law. So this concern with the homogenization of Stokes equation on a perforated domain. So let me first describe the problem. So we have a stationary linear Stokes equation in a domain omega. I'm going to describe how this domain omega epsilon is constructed. So we have a right-hand side a forcing term f. So this is the standard Stokes equation. Mu is the viscosity constant. The constant mu is irrelevant here, so you can assume mu to be 1 here. The epsilon is the period of the domain, and also roughly the size of the solid obstacle. So one thing I want to point out here is that the velocity has been normalized by a factor epsilon square due to the existence of obstacles. The velocity actually is in the order of epsilon square. It's fairly small. So we're going to just put, for convenience, we'll put a constant epsilon square before this Laplacian term. So the true velocity here is epsilon square times u epsilon here. So that's the problem we're going to consider today. So this equation is system is used to describe flow in porous media. So you have rocks sitting here, and the flow goes between the solid obstacles. So of course, the situation I'm considering here is the ideal situation. You have this obstacle periodically arranged. So let's be more precise to describe how this perforated domain omega epsilon is constructed. So let's say we have a unit cell Y. Inside we have a solid part, which is denoted by Y sub S, S for solid, and the remaining part will be the fluid part, YF, and we're going to assume that YF is connected. This is important, but also the distance between the boundary of the solid to the boundary of the cell is positive. This is not important. You can get away with this assumption, but here we're going to do that with the assumption for the convenience. So that's the picture on each unit cell. And then we're going to construct the domain omega epsilon. So omega is a bounded domain in RD, and we cover the space by a mesh of size epsilon. And then for each cube of size epsilon, which lies entirely in the domain, we remove a obstacle of size epsilon. So it's a raised scale here. And if the cell touch the boundary of omega, we do not remove obstacle. So in this way, we have the whole boundary of omega intact. So the boundary of omega epsilon consists of two parts: the boundary of omega, which is still there, union the boundary of obstacles, which I denote by gamma epsilon, which lies entirely in omega, but also has the property that the distance from gamma epsilon to the boundary of omega is at least a small constant times epsilon. Okay, so this will be useful later on here. All right, so for each epsilon, you're given an f, and omega epsilon, of course, is a bounded domain. You can solve the Stokes equation. You come up with a weak solution in H1 0 of omega epsilon for the velocity, and the pressure is a L2 function. To fix the pressure, you can assuming the mean value is 0. So because the solution vanished on the boundary of obstacle, it's natural to just extend this velocity into the obstacle by 0. So now you have a domain. So now you have a function which define on whole omega. Okay. So the extension of the pressure term is a little bit tricky, but it can be done. It's not by 0. There is an explicit formula, and the extension is denoted by capital P epsilon, which is defined everywhere in omega. Because we're going to talk about convergence, we need to have the sequence of functions defined on the same domain. So it can be proved that as epsilon goes to 0, the extension U epsilon, still denoted by U sub epsilon, converge to a function in L2 weakly. And the extension of the pressure, capital P epsilon, converge to a function strongly in L2, And moreover, the limiting functions U0 and P0 is given by a Darcy law. Remember here, this is the rescaled velocity. So the Darcy law simply states that the flow rate is proportional to the balance of the forces. So you have a force F given in the right-hand side. The gradient of the pressure generate also a force. The capital K here is a symmetric positive matrix, which I'm going to describe in the next page. And mu is the cosmic constant here. And so the first equation is that the limit U0 is given by this formula in omega, everywhere in omega. The divergence is preserved in a weak convergence. And furthermore, U0 dot n equal to 0 on the boundary of omega. Okay, so initially I have U epsilon equal to 0. And here in the limit, you only got the normal components of U0 equal to is 0 on the boundary. So this actually is an elliptic equation. So the way to see this is that you plug the first equation into the second equation, and you see that that just gives you a elliptic equation for P0 with the right-hand side divergence of mu inverse KF. And the last equation just give you the Neumann problem for that elliptic equation for P0 on the boundary of omega. So this the Neumann problem has a unique solution up to a constant. So the limit is uniquely defined here. That is the Darcy law, the classical Darcy law. So this Darcy is a French engineer in the 19th century, and of course we're talking about a modern version of the Darcy law here. So next I want to describe the cell problem, the correctors, and also talk about this this matrix capital K, so-called permittivity matrix, how it's defined. So here we have a cell problem. So you have a unit cell Y, you remove an obstacle, and you solve the Stokes equation with the right-hand side E sub j, that is the unit vector, divergence of Wj is 0 in the fluid part with boundary Dirichlet boundary value on the boundary of the obstacle and periodic boundary condition on the boundary of the cell. Okay, so that's the cell problem for the Darcy law, and the Wj, pi j will be called correctors. They are one periodic functions, periodic with respect to the integer lattice here. Okay, so and then we simply average this corrector function on the cell, and remember that you can extend this function W by 0 into the whole cell. This should be regarded as average of the extension on the unit cell here. So that is the matrix K. It's Kij is given by this average. If you use the Stokes equation, you can easily see that it's given also by the integral of the gradient of Wj dot the gradient of Wi. The index L is summed. So that shows that this matrix K is symmetric, and it's also positive definite. And so that is the constant matrix K in the Darcy law. And so this gives you a constant elliptic equation in the domain omega with the Neumann boundary value problem. All right, so the Darcy law can be derived using formal two-scale asymptotic expansion. That's probably done in the 60s, 70s. The first rigorous proof was given by Luc Tata in 1980 using his energy method, a method of oscillating test function. There is an explicit formula later for the extension of the pressure term given by Lipton and Avalinda there. And in 91, Allaire observed that you can actually prove strong convergence if you subtract the leading term in the asymptotic expansion. So this is different from the classical case when you have a single elliptic equation or elliptic system where the leading term does not depend on y. Okay, so in this case, the leading term does depend on the fast variable, and therefore you don't get a strong convergence of u epsilon to u0. You get a weak convergence, but if you subtract the leading term with the fast variable, so that this is just the first term in the leading in the asymptotic expansion, you have strong convergence in L2, and you can see that just remind you again that the average of this corrector Wy is this constant matrix K. Okay. So this was done using the method of two-scale convergence. Okay. So the problem I want to describe today, the problem I've been interested in for the past 10 years, is so-called quantitative homogenization. So from the qualitative homogenization, we know the solution has a limit, and the limit satisfy certain equations. Here we'll be concerned with the precise or sharp convergence rates. So for instance, we do know the difference of u epsilon and its leading term in the asymptotic expansion converge to 0 in L2 strongly. And we also know that the extension of the pressure converge to a function L2. And so the question we want to ask is that what is the convergence rate? Better, what is the sharp convergence rate one can prove as epsilon goes to 0 there. Another class of questions concerning the regularity, we call the large-scale regularity. That is the regularity of solutions that are uniform with respect to this parameter, small parameter epsilon. So lots of work has been done in the last 10 years and for elliptic equation, also in the classical periodic case, but also stochastic case. But here we want to talk about this kind of questions for the classical Darcy law here. So here's the theorem on convergence rates. So we are assuming the domain omega is C2 alpha for some alpha positive. We're assuming the obstacle is C1 alpha. We're assuming that the right-hand side, the function f belongs to C1 1/2 or C3 halves, and the dimension greater or equal to 2. Then we can prove that the convergence rate for the solution, U epsilon, and also the convergence rate for the gradient of the solution multiplied by epsilon. So this will be the leading term in the asymptotic expansion for epsilon times the gradient. And the extension of the pressure minus its limit, all this in L2 norm is bounded by constant times the square root of epsilon multiplied by the C1 1/2 norm of f. For any epsilon between 0 and 1, the constant C will depend on mu, the obstacle, and as well as on the domain omega. So that's a theorem on the convergence rate. Later on, we'll mention some result on the regularity problems. Okay. So before we get to that, I want to remark that first of all, the square root rate is the best you can do. This still is because of the fact that the solution vanish on the boundary of the obstacle. I'm sorry, the solution vanish on the boundary of omega, where this leading term in the asymptotic expansion does not. So this function Wx of epsilon actually oscillating near the boundary of omega. And this oscillation generate a boundary layer of thickness epsilon, and that automatically counts for the square root of epsilon error term there. Okay, there is a previous work on this problem in a two-dimension case. It was done by these two mathematicians, and they proved that in a two-dimension case, you can prove a rate of epsilon to the 1/6 using a string function which only works in 2D, and of course the rate 1/6 is not sharp. That construction cannot be extended to higher dimension case. Okay, but I also want to mention that there work for the case of Laplacian with the Dirichlet condition. They also work for the Stokes system with Neumann boundary value problems on perforated domains. The Neumann boundary condition on a perforated domains it's quite different from Dirichlet boundary condition. So in that case, because you're assuming, for instance, the Neumann data say vanish on the boundary, there is a natural extension. You can extend the solution into the obstacle without causing much singularity. Well, in the Dirichlet case, you have to extend by 0, and that's create lots of problems as far as the regularity is concerned there. Okay, so I will mention several ideas in the proof of this theorem, particularly the construction of two correctors to handle this discrepancy of boundary value of U epsilon and the boundary value of the leading term on the boundary of omega here. So let me point out that so U epsilon is the solution, U0 is the leading term. It's given explicitly with this corrector. I mean, both of them vanish on the boundary of the obstacle. So the difference will still be 0. That's not a problem. The problem is on the boundary of omega, where U epsilon is 0 and U0 is not. So you have a kind of oscillating boundary data on the boundary of omega. And in order to handle this problem, we're going to construct two boundary layer correctors. One deal with the tangential boundary part, boundary data, another for the normal boundary data. And there's also a interior corrector for the divergence operator, but this is known already in the previous work. So I will say more about this boundary correctors. And so it's kind of interesting to point out that the tangential data has to, the normal data has to be treated differently from the tangential data in the Darcy law case. And this will be clear when you deal with non-homogeneous boundary conditions for the Darcy law. The limiting equation will only be concerned with the Neumann, the normal components of the data, of the boundary data there. Okay, so let's first look at the tangential corrector. So what I do is that I look at, I simply solve a Stokes system in the perforated domain, omega epsilon, and with the tangential boundary data of the difference. So that will just be U0 x over epsilon minus its normal part. And therefore that this data that the normal vector vanish on the boundary. Okay, so this part actually is fairly easy. So we can prove this lemma. You look at the L2 norm of the corrector, or epsilon times L2 norm of the gradient. These two terms are in the same order. So if you can control the first term, Poincaré inequality. And so this give you the square root rate times the C1 norm of F. So this is this simply you do is that you just using the energy estimate, multiply both sides by psi t, and you have this equation. So the left-hand side is what you wanted to control the gradient L2 norm times epsilon. And the question is, how do you handle the right-hand side? And here we're going to use something called a radic estimate due to Phipps, Koenig, and Vokoda in a 1988 paper for the classical Stokes system in a fixed domain, which allow you to control the normal derivative by tangential derivative. So that's the idea. So nothing more than that. So you just simply cover the boundary of omega by all neighborhood of epsilon. On each small neighborhood, you apply a rescaled radic estimate. and that's all you need to handle the tangential corrector. Next, let's look at the normal corrector. So we solve a Stokes equation with the boundary data, just the normal components of the discrepancy. So, but there is a compatibility condition always for the Stokes equations generated by the divergence-free equation. So here we need to minus a constant gamma, and so that the compatibility condition is satisfied. So this constant will not cause any trouble in the computation there. Okay, so that's the definition of normal corrector, and here is the estimate we need. It's the same type of estimate as the tangential corrector. So all these norms is bounded by square root of epsilon times the C3½ norm of omega. Okay, so roughly the proof involve energy estimate and as well as the non-tangential maximum function estimate due to Phipps, Koenig, and Vokoda in the same paper I mentioned before. And finally, a integration by parts argument on the boundary of the domain, which I'm going to be the most interesting part of this proof. Okay. All right. So here is the key observation for the proof of this lemma. So we look at U0 dot n, the normal components of the discrepancy, and we use the boundary condition in the Darcy law, so to subtract the average of the corrector, which is denoted by capital Kij, right? So that Darcy law on the boundary just tells you that K times F minus the gradient P0 is 0. So we're using the boundary condition for the Darcy law. Once you subtract the average, of course, the mean value is 0. And we also know that this corrector is divergence free. And these two conditions allow you to rewrite this corrector minus its average as a divergence of a tensor which is anti-symmetric or skew symmetric. So I have phi I L j. J is fixed. If I switch I with L, I got a minus sign. So this for fixed j, this matrix phi I L is skew symmetric, and that's a key here. Okay, and you can do this for any a vector with this property: mean value 0 and the divergence free. Okay, so this skew symmetric property will allow you to write this normal component as a tangential derivative of this tensor phi times f minus the gradient of P0. Okay, so what I see here is that you look at this second term here. If you switch I with L, you generate a negative sign which cancel this one, and then therefore it can combine with the first term, and that's where the 1/2 coming from. Okay, so the point is that you look at this derivative on the boundary. You have I and L, you have L and I, and therefore this is a tangential derivative on the boundary of omega. And so when you have this tangential derivative on the boundary of omega, when you integrate this function, this normal component against another function on the boundary, you can do integrating by parts. That you can bring the derivative, this tangential derivative, to the function you are integrate against. And this, of course, also generate this factor epsilon, which I needed. Okay, this epsilon coming from, because if you take the derivative of phi x over epsilon, that will generate 1 over epsilon on the, and I need the epsilon to cancel out. So that's how you come up with decay factor. So that turns out to be the key observation to make this work. And so let's see how do you use this observation to show that the Neumann, the normal boundary corrector have the right decay. So here is the energy estimate for the Stokes equation on a domain omega, and so you have F, capital F, G appeared. The capital H is an extension of little h into the domain omega. So all you do is you just simply choose a capital H which agrees with little h on the boundary. And how do you choose capital H? And so that certainly we can use the solving a Stokes system on omega. Okay, no epsilon, so just fixed domain omega. So a capital H has the right boundary value, and gamma is again it's some constant which determined by the compatibility condition of the Stokes system. Yeah. Okay, so looking at this energy estimate, you're gonna when you plug the difference of the solution and the leading term into the Stokes equation, you're going to generate some F, capital F, and the G, which you have, which you can handle here. So the one problem is that you don't see any possible decay from capital H, because H here is just the L2 function. The boundary value is a small h there. Okay, so that's a problem we need to handle using the previous observation. So h has the boundary value is given by this function on the boundary of omega, and previously we noted that the boundary data actually can be written as a tangential derivative. So now we want to estimate L2 norm of h on omega here. And for the gradient of h times epsilon, this just can be handled by energy estimate. So that's not a problem. The problem is for the L2 norm of h. So you're going to divide omega into two parts near the boundary. And because this is a layer of size epsilon, and so we can use so-called non-tangential maximum function estimate to push the integral onto the boundary. And so because the thickness is epsilon, so that generates automatically epsilon to the 1/2. And now you have to deal with the interior part. In the interior part, we're going to use the Green's function representation, as well as the fact that you have a tangential derivative. So for points away from the boundary, you write your solution as a Green's function times this boundary data. And then you bring this tangential derivative to the Green's function. So you do an integration by parts on the boundary of the domain. And that's how this the rates coming from. So we using this observation to handle the parts that's of capital H away from the boundary of omega. All right, so I mentioned before, there's also an interior corrector that's already known. So one thing we did here is that we do a suitable smoothing of this F minus gradient of P0, and this will allow you to trade the order of the derivative with the order of decay. So that's a minor point for the interior corrector. All right, so finally, you simply put in everything together. So you subtract the leading term, but also subtract these two boundary correctors and the interior correctors. You put this function V epsilon into the energy estimate, and you got what you needed. So the condition on the boundary of omega is required in order to guarantee certain regularity of P0, and the condition for the boundary of the obstacle are used in order to guarantee certain estimate for the gradient of the pressure term, gradient of the corrector term. Okay. All right. So we can also prove deal with a non-homogeneous boundary data. That is, you assuming u epsilon equal to some function b on the boundary of omega. The Darcy law in this case becomes the first two equations are the same, but the boundary condition is given by b dot n. So that's I mentioned earlier. The limit u0 only depend on the normal components of the boundary data b there. Okay, and so for this non-homogeneous boundary data, there's the same proof also gave you the sharp convergence rate, and so now you here I have actually have three terms: L2 norm of B, and actually you can do better for the tangential part of the boundary. So they're in the same order, but you have extra epsilon for this last term. All right. Any questions?
Could you explain where did you use the C11 half condition on it?
Well, it's coming from the requirement for P0, the regularity requirement for P0. So here, so P0 appear in this equation, and in order to say P0 in C2 1/2, you need to require F to be C1 1/2. It's not clear. This is sharp. I don't know it.
Okay, thanks.
Some conditions on that. Okay, so in the rest of this talk, I'll talking about a large-scale interior estimate. So here we'll be talking about the interior estimate. No boundary estimate yet. So you have a unit cell. Just review the solid part, fluid part, and then we just extend the fluid part to the whole space. So I denote this by omega, lowercase omega. That will be an unbounded domain and one periodic domain called omega here. All right. So let's say you take a cube of size r, and r greater equal to epsilon, and then we just call the intersection of this cube with this rescaled epsilon omega domain by qr omega. Something is wrong here. I probably should call qr epsilon. So this is a typo. That means qr epsilon. Okay. Okay. So again, omega, small omega is an unbounded domain. Just unit cell remove the obstacle and then just repeat itself. And then you look at a large size cube and take the intersection with small omega. Okay. So we can prove the interior Lipschitz estimate. So you have a solution. So this is an interior problem. Let's take there's no boundary omega here. So we solve the Stokes equation. Again, the same normalization epsilon square here. And u epsilon equal to 0 on the boundary of the obstacle. We're not assuming u epsilon equal to 0 on the boundary of the QR. Just there's 0 on the boundary of the obstacle. So that so F is in C alpha for some alpha positive. And then we can show that you take a cube of size small r between epsilon and capital R over 2. We cannot go down below anything below epsilon. That will be a local estimate. So this is a large scale estimate for R greater or equal to epsilon. Then your average is solution on any q little r. It's bounded by a constant times the average over q capital R plus this term depend on F, C alpha norm times the right scaling factor R to the power R here. And you can also average the gradient, but you have to multiply by epsilon. They are bounded by the same right-hand side. So this is what we call a large scale Lipschitz estimate. Okay. So the constant depend on mu, alpha, and this obstacle y sub s. There's also a C1 alpha estimate, provided you subtract the leading term in the asymptotic expansion. And this is also referred as the excessive decay estimate. So you look at the solution u epsilon, you subtract this leading term. Well, the leading term there you can replace by a constant, and you're searching for the best constant, which for this average. So E here is a vector in RD, and u epsilon minus this corrector multiplied by some corrector is a matrix, so acting on a vector E here. And this gives you a decay if R is less than capital R. So R here again is between epsilon and R over 2, and this is the same term as in the previous theorem. So for the derivative, you again multiply by a small epsilon by the same epsilon, and this all becomes the leading term. And so this E again is a constant. So you take an infimum over all such constant that give you the so-called C1 alpha estimate, or maybe C1 beta in this case, because beta has to be less than alpha. So this estimate is true as long as you don't need much regularity for the boundary of the obstacle. But if you do have some regularity for the boundary of the obstacle, let's say C1 alpha, then you can combine the large scale with the local, with a small scale or local estimate to obtain true Lipschitz estimate. So the L infinity norm plus the L infinity norm of gradient multiplied by epsilon is controlled by the L2 average plus the term involved the right-hand side. And there's also a corresponding large-scale estimate for the pressure term, which follows from this estimate for the velocity simply by using Katropoli inequality for Stokes equations. Okay, So we can also prove W1P estimate. I'm going to state the theorem in the next page for the whole for the unbounded domain epsilon omega. And if the boundary is CK alpha, then you can have a uniform WKP estimate. This result was announced by Mahmoudi back in 2005, but no proof ever appeared. Okay, so this is the W1P estimate. So we're assuming the boundary of obstacle is C1 alpha. Because P is used, I'm going to use a Q. So Q between 1 and infinity. We take a F in W1Q. Let's say. Well, yeah, this is a typo. Capital F is in LQ, I believe. Yeah, that's not right. So small f is also a Q function. Then we can solve this equation in the unbounded domain, periodic domain, omega epsilon, with Dirichlet condition on the boundary of the holes. And the key is the estimate. So the LQ